we've got two kinds of logarithms that we focus on. We've got the natural log, and we've got common logs. A natural log is in base E, and E is a number on your calculator, depending on what calculator you've got. So in my case, I'm going to press the yellow button and the natural log, and then e to the x will show up. So if I just want e to the first, because any number to the first power is itself, you will see that this is 2.718282, blah, 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 blah. So 2.718282. Actually, I just rounded that, sorry. 828182. 182, and it goes on and on and on for all eternity, never ever ever stops, never falls into a pattern of repetition. So it's kind of like pi. Pi's job is to play with circles. E's job is actually to play with money. Common logs are in base 10. Okay, and it's because we operate in base 10. So what's the smallest amount of money we have? We have a penny. Times 10, we have a dime. Times 10 is $1. Times 10 is $10. Okay, so we operate in base 10. There are other bases out there. So the examples that I've been giving you, here's log base A. That is not a common log. That is not a natural log. That's just a log. Okay. We had base 11. So this is not a common log. This is not a natural log. This is just a log. So why do we have common logs and natural logs? Because both of these have buttons on your calculator. So if I've got ln, means the natural log. And if I have log, that means the common log. So why isn't it NL if it's the natural log? Because we got it from the French, and they flip-flop their nouns and adjectives from what we do. So this is the natural log, and this is the common log. So this is base 10. Notice that if I hit the second key, I've got a base 10 with an exponent. This is base E. Notice if I hit the second key, I get the base E with an exponent. So what we're going to be doing in this section is just a ton of calculator work. So can we enter this stuff in our calculators? And that is what our question is. So going into looking at what you need to do. Hang on one fat second. I've lost control again. Okay, so what I'm looking for is, can I enter this in my calculator? So I would like to know if I have log of 342 times 28. Okay, can I enter that in my calculator? Well, what base is it in? If your base isn't written, it is either a common log, which is base 10, or it is a natural log. Well, this says log, and there's no base written, so it is implied that it is base 10. So can I enter this in my calculator? Yes, I can. I can hit the common log button, and then 342 times 28. 342 times 28. Close your argument, and then hit enter. And you find out that your answer is 3.981. Okay, 3.981. We're supposed to run to 4 decimal places, so 3.9812. So 3.9812. So basically, 10 to this power will give you whatever that product is. Okay? So let's try another one. We've got log of 305 plus log of 29. And so here's the deal. I can do this one of two ways. I can enter it just the way it stands, or I can say I've got two separate logs joined by addition. So I could write that as a single logarithm joined by multiplication. Either way, you're going to get the same answer. So let's look and see. No base is written, so it's either natural log or common log. So that we're in log, so it's common log. So I've got the log of 305, close your argument, plus the log, where'd it go, of 29, close your argument, and I get 3.9467. So 3.9467. So again, 10 raised to, if I add those together and raise 10 to that power, I'll get that answer. Now look at this. If I do the log of 305 times 29, close that argument, I get the exact same answer. Okay, so we are just showing you that also that these log rules work. So I can add them together or I can squish it together. Either way, I'm going to get the same answer. So let's do it again. I've got the log, or the common log, of 502 minus the common log of 304. And so what is my answer? We'll also realize I could write that as the common log of 502 over 304. Okay, using properties of logarithms. So what do I get first? I get the common log of 502, close your argument, minus the common log of 304, close your argument, and I get 0.2178. So 0.2178, well, what happens if I had condensed first? If I'd condensed first, then the log of 502 divided by 304 is that exact same answer, 0.2178. Okay, so it just really depends on how you want to enter it. So the next ones that we have, now we got some word problems. So I have the formula for the pH of a solution of hydronium ions is given by the following logarithmic equation, where I've got the negative log of the positive hydronium ion concentration, where this part right here is the hydronium ion concentration. Okay? So find the pH of a certain agricultural product with a hydronium ion concentration of, so my H3O plus is 3.1 times 10 to the negative 5. Okay, and I want to round this thing to the nearest tenth. So what I have is, I'm told what my hydronium ion concentration is, so I just need to plop it in here. My pH, therefore, is negative common log of 3.1 times 10 to the negative 5. Do you see any variables in there? No, you do not. So slap that thing in your calculator. So we have the negative common log of 3.1 times 10 raised to the negative 5 power. And then I'm going to close that argument, and I'm going to get 4.5. So my pH is 4.5, which is acidic. Okay, my pH is 4.5, which is acidic. So let's do it again. We have the pH of a fruit juice is 4.9. So now we're going to go backwards. I'm going to use the same setup where the pH is negative common log of H3O positive. I don't even know how to say that. I'm hoping. All right. So what I have is the pH is 4.9. And so I am trying to find out what the rest of this mess is here. So remember, this is just a really weird variable. Okay? So that's not, we're not solving for H. We're not solving for this little sub 3 or those O's or anything. This is a clump. This is one thing. So what I would like for you to do is flip-flop. So I've got a negative log of this hydronium ion concentration, and that's going to equal 4.9. Why do I want you to flip-flop it? Because I brainwashed you in the last section to where if I've got a log on the left and something else on the right, I can change it into exponential and solve from there. So remember, I'm in base 10. Well, I want my log to be by itself. So I'm going to divide both sides by negative 1. So now I have the common log of my hydronium ion concentration is negative 4.9. And now I can do my backward circle. So 10 raised to that power is going to equal the hydronium ion concentration. Do I have any variables? No, I do not, which means 10 raised to the negative 4.9 is going to give me 0.1234 zeros 12, 5, 8, 9. 3, 4, 12, 5, 8, 9. So we need to put this into scientific notation. So this is a tiny number. We're going to have a negative exponent. So how many times do I need to move my decimal place? 1, 2, 3, 4, 5. So you want to move that decimal point. Move that decimal point until you get just past a number from 1 to 9 inclusive. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I moved it. I didn't want a 0. I wanted a 1. So what I have now is 1.2589 times 10 to the, since I moved it right, it's going to be a negative exponent. So how many times did you move it? I moved it 1, 2, 3, 4, 5 times. So negative 5. Okay? And then we're rounding to the nearest tenth, which is going to be 1.3 times 10 to the negative 5. Okay? So scientific notation rears its head. Okay, so if I have a wetland has a pH between 6.0 and 7.5, it's a rich fen, poor fen, it's a bog. Suppose that the hydronium ion concentration of a sample of water from wetland is 7.7 times 10 to the negative 7 moles per liter. So how am I going to classify this thing? So my pH is once again a negative common log of the positive hydronium ion concentration. And so what I have is the positive hydronium ion concentration that I'm given is 7.7 times 10 to the negative 7 moles per liter. So how am I going to classify this wetland? Is it a rich fen, a poor fen, or a bog? I don't know. So we're going to slap this thing in for this right here. So my pH is going to be a negative common log of 7.7 times 10 to the negative 7. And then again, do you see any variables? No, you do not. No, you do not. So negative log 7.7 times 10 raised to the negative 7 power. Make sure you're using negatives and not subtraction. And I get 6.1135. So 6.1135 is the classification for the pH that I get. So I find out that that is between 6 and 7.5. So this is classified as a rich fen. I don't know what that means, but it's a rich fen. All right, so find the value. Now we're going to hit natural logs. So I've got the natural log of 82 over 20. And this is just going to be a long video. I'm not going to do 2 of them because we're almost done. All right, so this says now I've got the natural log, which means my base is E. And so I'm going to poke the natural log button and do 82 divided by 20. And that gives me 1.4109. So 1.4110 is what it went to when I rounded. Now, what could we have done? Because I'm trying to get those properties of logs in your head. I could have done the natural log of 82 minus the natural log of 20. If it's division on the inside, it's subtraction on the outside. So that would have been natural log of 82 minus, that's why you should always close your argument, minus the natural log of 20. And I get 1.4110, which is what I had this way. Okay, so the natural log of 30 plus the natural log of 976. So I can find this. Now what could I enter? If it's addition on the outside, it'll be multiplication on the inside. So I've got the natural log of 30, close your argument, plus the natural log of 976, close your argument, and I get 10.2847. 10.2847. Why am I doing little squiggly lines instead of equals? Because I'm rounding, so it's not an exact answer. So that says approximately. I could have done a natural log of 30 times 976, and I could have gotten the exact same thing. Okay, 10.2847. So we're just practicing. I don't care which way you do it as long as you do it right. So find the value. We have the natural log of 88 minus the natural log of 22. And again, I can put those in parentheses. And if it's subtraction on the outside, oops, I just put the answer. It's division on the inside. Okay, so I can have the natural log of 88 minus the natural log of 22. That gives me 1.3863. And then what happens if I just rewrite it as a condensed logarithm? I would have the natural log of 88 divided by 22, which I could just put the natural log of 4. Because 88 divided by 22 is 4. So I get 1.3863. And then if I do the natural log of 4, which is 88 divided by 22, the natural log of 4 is 1.3863. Okay? So all of those will give you the same answer. All right, then I have geologists sometimes measure the age of rocks by using atomic clocks. By measuring the amounts of potassium-40 and argon-40 in a rock, the age, T, of a specimen in years is found by the following formula, where A and K are the numbers of atoms of argon-40 and potassium-40, respectively, in the specimen. So I'm given this heifer thing. So T equals 1.26 times 10 to the 9th. Close that. And then we have the natural log of 1 plus 8.33 times A over K over the natural log of 2. Okay. So it says, I want to know what the sample's age is. So I'm solving for T. So notice there's no variables here. There's no variables here. Oop, there's a variable. Okay, there's no variables here. So A over K is the only thing I'm missing. And it's telling me that A over K is 0.143. So what I'm going to do is sub in. So I've got 1.26 times 10 to the 9th. And then I have the natural log of 1 plus 8.33 times 0.143. And all of that is over the natural log of 2. Okay? So all we have to do is throw that thing in our calculator. So I'm going to go ahead and use parentheses just to keep things clear. So I've got 1.26 times I said, 10 raised to the 9th power. And then I'm going to take that times this numerator. So times, parentheses again for the numerator, the natural log of 1 plus 8.33 times 0.143. Close that. And then divide by the natural log of 2. And hopefully, all right, so I get, goodness, I get 1425.96. This is a big number. 1425.96 to the nearest thousandth as needed. Hang on, I'm pausing you. Okay, sorry. It threw me off because it wanted the nearest thousandth as needed, and then I was like, thousandths? I'm getting a really big, huge number. Okay, because this is, there's 100,000s, there's millions. So what you have is your hundreds, your thousands, your millions, and your billions. So we're reporting this as 1 point to the nearest tenth, 1.4 billion years old. I was like, what? That is not what I got. Okay, so that's what was on my calculator. Okay, and when I look down here, the first three are going to be your hundreds, then your thousands, then your millions. So I've got 1 billion and some more. So when I round it, I get 1.4 billions. Actually, it says to the nearest thousandth. I thought it said to the nearest tenth. So the nearest thousandth is going to be 1.426 billion years. Sorry, that threw me off. Okay, last one in this section is the logarithmic function. F of x equals negative 100 plus 80 times the natural log of x. Models the number of visitors in millions to a certain country's museums, where x is the number of years since the initial recording of the number of visitors. Use this function to find the estimate of the number of visitors in year 45. So in year 45, if this measures years, and that tells me how many, then what I'm looking for is negative 100 plus 80 times the natural log of 45. So hit enter and I get 204,533. So writing this out, I would have had negative 180 times the natural log of 45, which gave me approximately 204.533 million. And that is this section.